I've got a new vector field up on the board over here, okay, and I just named the component functions P and Q, as the book usually does. Okay. What I want to do is two things. I want to first of all verify that this is conservative, and then I want to find a potential function. And what I've done is over here written down the steps for finding a potential function, because we did that in the last video, but it was such a long problem that it was a three-step process, and I think step 1 got written and it got erased before I wrote step 2, and then that got erased before I wrote step 3, so I just sort of wanted to have them all in one place. Let's start though by verifying that this is actually conservative. Looks like the domain D is all of R2, and that is simply connected. I like to start by pointing out that my region is simply connected because it's so easy to forget to do that. But if the region is not simply connected, we don't know, even if the condition is satisfied, whether it's a conservative vector field. Okay. So now I say, okay, if it's conservative, that's already the partial with respect to x. So to get to a mixed partial, I would take the partial with respect to y. So if I do that, looks like I'm going to just get cosine of y. The 2x will drop out. Here, I'm going to take the partial of q with respect to x, and that's going to give me cosine of y. Those are the same. I'm working on a simply connected region. Those things together tell me that f is conservative and on all of R2. Excellent. So now I want to find a potential function. Okay. So we're basically going to go through this three-step process. I now know that p is the partial of f with respect to x. So I can integrate it with respect to x, and that's going to give me a partial formula for my potential function f. Of course, that's just one of two options. I could also integrate q with respect to y. I've just written this out as if we're going to choose p with respect to x. Once I've done that, now I want to take advantage of the fact that I know that this is the partial with respect to y. So I'm going to take the partial with respect to y of the result from step 1 and say that's a formula for the partial of f with respect to y. But I also know that q, what I have right here, is a formula for the partial of f with respect to y. So I can set them equal to each other. And there should be some term that just involves y, because when I integrate here, my constant of integration is going to be a function of just y, which I'll call k of y. So when I take the partial, I'll get a k prime of y. I can solve for that in this step, and then I'm going to integrate again. So I'm going to integrate just k prime of y to get k of y, to get that one piece that I wasn't sure of, and then I can put the pieces together and I'll have f. Okay. Now, I like this. I think this is the most straightforward option. Your other option, I will just point out, you could integrate p with respect to x, and then you get some formula plus a function of y. You could then integrate q with respect to x, and you get some formula plus a function of x. And then you can sort of say, okay, now these guys have to be equal to each other, and you can sort of figure out what your function of y and what your function of x has to be in order for those to be the same. I prefer this just because taking the derivative tends to be easier than integrating. Okay. And while I do have to integrate again, I'm integrating just a very small piece by the end of this. So that's usually what I'm going to do, but sometimes students ask, why can't we just integrate both sides and then make it match? Totally fine. You can. Okay. So I'm going to say f is an integral of the partial of f with respect to x dx, and that's just p. Okay. So we're going to integrate sine y plus 2x with respect to x. So this is constant with respect to x, so I'm going to get x sine y plus x squared plus k of y, a function of y which would be constant with respect to x. All right, so now I can say the partial of f with respect to y is the partial with respect to y of this formula that I've just found. So here, that's going to give me x cosine y Derivative of x squared just drops out, plus k prime of y. And again, that's the one place where the prime notation is okay, because k is a function of just one variable, y. Okay. But now I can use the fact that I know that q is the partial of f with respect to y. And in fact, label these guys if I want to. Okay. So that's got to equal q. So I know that x cosine y plus k prime of y is equal to x cosine y minus 1. Subtract x cosine y from both sides, and k prime of y is equal to negative 1. That doesn't have any x's in it, so I can keep going. Again, if at this point you get x's in your formula, you have made a mistake. Don't keep going. Because if you keep going, that signals that you don't understand conceptually what's going on, that this is supposed to be something that depends just on y. Turns out it's actually a constant, okay? But if there were x's in it, it would not be constant with respect to x. Okay, so now I'm going to integrate. I'm going to say k of y is an antiderivative of k prime of y. So we're integrating negative 1 dy. That's going to give me negative y plus c. And the directions, I just gave them verbally, but the direction said to find an antiderivative. So I'm going to just choose c equals 0 so that k of y is negative y. You should write the plus c and then state that you're making that choice. Because if I don't write it, I've just written this, and that's not true. Because this means the general antiderivative, which has the plus c in it. So do make sure that you're writing that. If you want to include it in your final answer, you can, but it's totally fine to just make the choice, since we just need an antiderivative, to just make the choice that you're going to have the antiderivative that has the constant being 0. But now I can say my potential function f of xy is x cosine y. Oh, sorry, I erased the wrong bit. It was, I erased what we had before. It was x sine y plus x squared plus k of y, which I now know is minus y. Sorry, I was starting to copy the partial with respect to y instead of what f was. Okay, but this is just putting the pieces together with what we had previously. All right, next video we'll take a look at why we need our region to be simply connected.